Let me just do a quick introduction to the heat equation, and then we can dig in more on Monday. Okay. So we're going to start by talking about the heat equation, and in particular how to get its fundamental solution. Okay. So kind of just like we had the Delamere solution for the wave equation, we're going to have a fundamental solution for the heat equation that allow us to build solutions in more special cases. Okay, so the heat equation, right? What's it given by? U sub t equals some coefficient k times the Laplacian of u, okay? It's also known as the diffusion equation, okay? And it's the prototypical parabolic PD, okay? At the beginning of the class, we talked a little bit about physical interpretation, okay, of this PDE. So in this case, for instance, consider some concentration U of xt, okay, of some substance, okay. Conservation implies the following, essentially that U sub t plus the divergence of Q, okay, of U is equal to 0, okay, where X is in some volume, okay. And this is from balance laws that we talked about a few lectures ago back in chapter 2, okay. So look back on chapter 2. So a constitutive law for this flux is that essentially it's going to move down gradient, okay? It's going to seek down gradient, right? And this makes sense if you release a gas into a room or something like that, it's going to spread out to where it's in lower concentrations. If you drop a substance into water, it's going to diffuse out to lower concentrations, so until the concentration is equilibrated, okay. All of this essentially says that flux seeks equilibrium, okay. If you're warm and it's cold outside, heat is going to leave your body. If you're heating a boiling pot of water, the heat is going to flow towards where it's cooler in the water, and it's going to heat the water up, okay. This is the standard sort of constitutive law, also known as Fick's law of diffusion, okay. And so as we said before, okay, we want D to be greater than 0, and D is our diffusion coefficient, okay. And sometimes we call this K, sometimes we call it D, okay. And it may depend on U, okay. We can handle some cases of that. And V is going to be the velocity of our medium here, although we don't deal much with advection diffusion in the next little bit. And so U sub t is equal to the divergence of minus d grad of u plus v u, in other words, u sub t plus grad dot v u minus d Laplacian of u is equal to 0, okay? And this is what's known as the Advection diffusion equation, okay? But if v is very small, then we're just going to derive the diffusion equation, okay? And we took k equal to d above, okay? And this is our diffusion slash heat equation, okay? So this is kind of the physical motivation, okay? And the problem that we'll solve on Monday is that of finding the fundamental solution. The fundamental solution to our standard one-dimensional heat equation PDE, okay, which is u of x 0 equals g of x and u sub t equals k uxx, okay? And the main tool that we're going to use is self-similarity of solutions based on the symmetry of this equation. So just like in the tail end of our analysis of the wave equation, we use the symmetry of those operators in order to work out a method for finding solutions. We're going to use symmetry in this case in order to find solutions to the heat equation, okay? And the idea is that you have, reflection and translation symmetry, and then you can get a function that you can kind of integrate against your initial condition, and that will tell you that, the solution to this IVP